make some plots. If you go to NASA's website, you can easily find out the period of all the planets. Can you guys see this? So you can see Mercury. So the unit I'm using here is a year on Earth, which is 365 days, Earth days, 24 hours. So Earth is having a period of 1 year, and this is the planets from sorting with the distance to the Sun. So the closest is Mercury, the farthest is Neptune. You can see that the period or the time it takes for the planet to go around the Sun is longer. A year on Neptune is 167 times longer than a year on Earth. And because we have a relation of period squared, so I need to figure out the period squared. This is the square of t. Now, this is the distance of each planet to the Sun. AU is a distance from Sun to Earth. So 1 AU is the distance from Sun to Earth, and the Sun-Earth distance is 1. So this is a unit defined by how far the Earth is to the Sun. So you can see that Mercury is closer, Neptune is 30 times far away from the Sun. And my plan is to plot t squared with r squared, and r cubed to see which one does t squared actually proportional to. And here's the plot. So this one, the one on the left, is t squared with respect to r to the power of 1. This is t squared to r squared. This is t cubed to r cubed. You guys see the plot? Good. So who thinks that t squared is proportional to r? Who thinks that t squared is proportional to r squared? Who thinks that t squared is proportional to r cubed? Good, so we know this should be r cubed. So n plus 1 should be 3, and n should be 2. So gravity here, so we know gravity is proportional to the distance squared and their masses. So let's just call the proportional constant to be capital G, m1, m2. And this capital G is the gravitational constant. It is a fundamental constant in nature. It is not like a small g. The small g will change depends on location. I'll tell you later. But that is how big gravity should be. We know it should be r squared because we can look at the planets, and you can actually do the same thing at home. Just go to NASA's website and look at the data. Okay? Now, if I write this proportional constant as g, then that g will go into here. Now this is an equal sign. And that g will go into here. This becomes an equal sign. And when I move everything to the other side, the g will go to the denominator. So now I can move this r cubed to the other side and get that the period squared over distance cubed of a planet should be a constant, which is 4 pi squared divided by g and the mass of the Sun. This is called the Kepler's third law. Kepler is a guy born before Newton, and what he did is to look at a lot of planets and analyze the data. he found that the plot is a straight line if you have t squared and r cubed, and he called that calculus slip law. He does not know what gravity is, and Newton wasn't even born yet. But now we know this relation is just a result of gravity. Okay? So if I square this 2, so for this 2, you need to memorize it. I mean, not here. I mean, so you need to memorize the fact that gravity is inverse proportional to distance squared, and we call this constant g. Then you can easily derive the calculus slip law. You don't need to memorize this. You need to know how to derive it, like what I did. And that's in your homework. But you need to know when I say calculus slip law, it is the thing that the period of the orbit and the distance of the planet is somewhat proportional. Okay? So that is the gravity between two particles. Now let's look at gravity at here, near the surface of the Earth. We said that gravity should be related to the distance between particles. But if we said for projectile motion, the acceleration is a constant no matter how high it is. The distance between the projectile and the ground is changing, but gravity is the same. The reason is that when you are standing on Earth, the gravity attracting you does not come from the ground. Earth is made with a lot of particles. There are particles from the ground. You have gravity between you and the particle. There's gravity between you and particle. So the ground will attract your body with gravity. That's true. But so does all the particles down here. These particles are far away from you, so the gravity is smaller. But there are a lot of them. If you just look at the particle that is 70 miles away from you, it only contains a small part of Earth, but 70 miles is already very long. In fact, the part of Earth that is 70 miles away from you generates about 90% of gravity that is pulling you down here right now. You don't need to know how to get this 90% or 70 miles. You need some math, but I did the math. Am I telling you the truth? 90% of gravity acting on you right now come from something 70 miles away. So if I jump up by 1 meter, the distance between me and the other part of the Earth is like increased by 1 meter compared to 70 miles. If you add 1 meter to 70 miles, your distance is still 70 miles. So that's why the gravity on Earth is basically the same no matter how high you throw a thing up above the ground. Because the distance between you and the ground is bigger, but compared to the distance between you and other part of the Earth, the change is negligible. So gravity on Earth will basically be a constant. And that comes from the gravity from all the particles. This is gravity from particle 1, gravity from particle 1, gravity from particle 2. The gravity acting on you right now is the gravity from all the parts of the Earth. And all of them should be proportional to your mass. They all have the mass in there. So you can take out the mass. The rest is a bunch of vectors acting together. You don't even know how to compute it, but you know it's going to be a constant, and it's a vector, and it's not going to change much when you are changing your height to the ground. So this is the gravity when you are near the surface of the Earth. When you go really far away into outer space, this will change, but if you're just jumping around on Earth, this is basically a constant because the distance to outer part of the Earth is not changing that much. Okay? And this is also why for projectile motion, you have the force of gravity equals your mass times acceleration, and mass cancels. So you get a constant acceleration for projectile motion. Once you throw something and the thing leaves your hand, the acceleration is just g going down. You know it's going down because Earth is symmetric, it is spherical, so it must go either into the Earth or out of the Earth. Gravity is attractive, so it's into the Earth. Okay? Now, gravity cannot be the only force between particles. If gravity is the only force between particles, everything will look like a solar system. You will just see a bunch of particles orbiting around each other. But when you look at this water bottle or the table, it doesn't seem like the particle making up then is moving or orbiting. So you know there must be some other force. We're not going to talk about what exactly those forces are, but we just need to know they exist. When we look at my bottle, it has a fixed shape. The shape is fixed, it's a solid. Something must be holding the particles together. If you look at my bottle in the microscopic level, it is made by a lot of particles. But the particles should not be orbiting around each other, but they should stay with a fixed relative distance so that they can maintain, so the bottle can have a fixed shape. So you know the interaction between these particles, besides gravity, should also have some spring-like force connecting them. They are forces, they are not springs. The world is made with only particles. I'm drawing a springs because the forces